In this session, we're going to explore probability. It's a big topic. We're only going to kind of dip our toes in it. This session is largely going to be vocabulary and notation with a little bit of computation. We'll start with some vocabulary. As far as vocab, we're going to be looking at experiments, outcome, sample space, and event. Now, these may or may not agree with what you think the words mean. Like experiment, you think of scientific stuff. In the realm of probability, an experiment is simply something you don't know the outcome to. And an example of an experiment would be like rolling a die, which, by the way, is singular for dice. An outcome, if the experiment is rolling a die, an example of an outcome might be rolling a 6. The sample space is just the set of possible outcomes. So for rolling a single die, the sample space would be getting a 1, 2, 3, 4, 5, or 6. And an event is basically like specifying outcomes. So an example of an event might be rolling at least a 4. So we can refer to like the probability of an event by saying, for instance, if a die is rolled, the probability of getting a 6 is 1 out of 6. You see, it's a fraction, it's a ratio. And of the 6 different possibilities that comprise the sample space, one of them is the number 6. So the notation kind of looks like function notation. So it's like p parentheses 6 is equal to 1/6. How about the probability of getting an even number? Since in our sample space we have even numbers 2, 4, and 6, the probability of getting an even number would be 3 out of 6. We reduce fractions, and so you have, it's a half. The probability of getting an even number is a half, right? You have a 50-50 shot. Now let's consider rolling 2 dice. If 2 dice are rolled, what is the probability of getting a sum of 6? To figure out the number of outcomes in the sample space, we actually are going to use the fundamental counting principle. So you have die number 1 and die number 2, and die number 1 has 6 sides, so there are 6 possibilities for that one. Die number 2 likewise, and so there are actually 36 possible outcomes. Of those 36, we could get a sum of 6 if the first die had a 1 and the second had a 5, or if the first die had a 2 and the second a 4, if the first had a 3 and the second a 3, which is the same thing as the first one having a 3 and the second a 3. Okay, you don't write that one twice. What are you talking about? I mean, the first die could have a 4 and the second could have a 2, and the first could have a 5 and the second of 1. And so, in other words, the 1, 5 it shows up twice, but that's just because it can happen 2 ways. 3, 3 can only happen 1 way, so we don't write it twice. That's all. So there are 5 possible ways to get a sum of 6. So of the 36 possible outcomes, there are 5 ways to get a sum of 6. And so the probability of getting a sum of 6 is 5 out of 36, 5/36. And of course, if that fraction could be reduced, we would do that. It's probably pretty clear to see that for any particular event, so the probability of E, some event, is going to be between 0 and 1. For instance, what's the probability of having a child and having it be either a boy or a girl? Well, that's going to happen. In most cases, we'll go ahead and call that 100% probability. What's the probability of a human having a child and it being an orangutan? That probability is going to be 0. Okay? So a 0 probability event will never happen. And I should probably remind you we're talking about the real world right now. And an event with a probability of 1 is a certainty. And of course, the closer you are to 0, the less likely an event is to happen. The closer you are to 1, the more likely an event is to happen. That makes perfect sense. And they say there's a 70% chance of rain. That's equivalent to 70 out of 100 or 7/10. You say, well, that's pretty close to 1, you know, better bring an umbrella or, you know, whatever. Now we're going to look at something a little more complicated to think about. Now suppose one die is rolled. What's the probability of getting less than 5? Well, if we look at the sample space, which is 1, 2, 3, 4, 5, 6, less than 5 would be 1, 2, 3, or 4, right? Not less than or equal to 5, but less than 5. So 4 out of the 6 outcomes are less than 5, which reduces to 2/3. And so we'd say there's a 2/3 probability that we're going to roll something less than 5. Now suppose one die is rolled again. What's the probability of getting an even number? We've already mentioned that. It's going to be 1/2. And I'm only repeating that so that I can ramp it up just a little bit and consider rolling one die, and what's the probability of rolling something less than 5 or an even number. What I'm going to do for ease of writing and notational purposes, I'm going to say rolling less than 5, I'm going to call that event A. And getting an even number, I'm going to call that event B. And so notationally, we're looking at the probability of A or B. And the mathematical symbol for OR looks like a U. It's a union, like between two sets, right? So mathematically, we're going to say the probability of A union B. Well, let's see. A Venn diagram would be a good way to go here. So I'm going to write, it looks like a MasterCard logo here. And in set A, I'm going to put all the numbers that are less than 5. And in set B, I'm going to put all the numbers that are even. Let's see, 1, 2, 3, and 4 are all less than 5. And 2, 4, and 6 are even. And you can clearly see that there's an overlap, right? 2 and 4 are both less than 5 and even. So it's not actually going to work out that it's the probability of A plus the probability of B. That's just not going to work because the probability of A rolling less than 5 we saw to be 2/3. The probability of B rolling an even number is 1/2. And if we add those two numbers together, we end up with something that's bigger than 1, and that's just not allowed. So what we actually have to do is we have to subtract off the probability that you're both even and less than 5. In other words, the 2 and 4, they got double counted. So we have to subtract out the probability that you're even and less than 5, which actually turned out to be 2/6 or 1/3. So when we subtract off that 1/3, right, which is could be considered the overlap, then we end up with 5/6. And if you look at the sample space, then you will see that of the 6 outcomes, 5 of them are either less than 5 or even. In symbols, we would say that the probability of A union B, or A or B, is equal to the probability of A plus the probability of B minus the probability of A and B. That upside down U looking thing is an intersection. And we can think of an intersection as the overlap, as we see in the case of the 2 and the 4. So this is just kind of a formula that you can, I don't know, try to memorize, but it just makes sense. You cut out the ones that you've double counted in the probabilities. If, by the way, the overlap turns out to be 0, like suppose the probability of A is even, right, and B is odd. The probability of getting both is 0, right? So if the intersection is 0, then you have something that's called they're mutually exclusive events, which I suppose I should write down in the next slide. And as it kind of sounds, mutually exclusive means that they just both can't happen. So in other words, yeah, they can't both happen. And then considering something like rolling less than 5 and rolling at least 5 are said to be complementary events. See, rolling less than 5 would mean 1, 2, 3, or 4. right? Rolling at least 5 would be 5 and 6. And as you can see, they're clearly mutually exclusive, and they represent the entire sample space. And so rolling less than 5 and rolling at least 5 are said to be complementary events. And if we call rolling less than 5 A, then rolling at least 5 is A. It looks like an apostrophe. It's the complement of A. It's all the rest of them. And we read that A with the apostrophe as A prime or A complement. I don't want you to think that all mutually exclusive events are complementary, because say rolling a 2 and rolling a 3, if we roll a die once, they're mutually exclusive, but they're not complements because they don't represent the entire sample space. Okay, we're going to turn our attention now to odds. Recall that if 2 dice are rolled, the probability that the sum is 6 is 5 over 36. The probability that the sum is not 6 is the complement of that event. And so it's actually the case that the probability is 1 minus 5 out of 36 because they are complements, which means they comprise the whole sample space. And so the probability of doing one or the other is 100% or 1. In other words, the number of ways that you can get a sum that's not 36 is 31. So the probability of getting not a 6, or not a sum of 6, is 31 out of 36. The odds, then, of getting a sum of 6, and maybe it's more accurately said, the odds in favor of getting a sum of 6, are 5 to 31. You see, we're just taking the numerators of the probabilities there. So we could also say the odds against getting a sum of 6, you reverse them, are 31 to 5. So if the first number is smaller than the second when you're giving odds, then it's not a likelihood that's going to happen. If the first number is greater than the second one, then there's a likelihood it's going to happen. And we do need to distinguish between odds in favor of and odds against. And so if you're trying to get a 6, the odds are not in your favor. And for our last example, we're going to see how we can get probabilities from odds. If a pollster says the odds against candidate A winning an election are 3 to 5, then what are the odds in favor of candidate A winning the election, and what is the probability that candidate A will win the election? I know, really original with the candidate A, huh? Okay, so the odds against candidate A winning the election are 3 to 5, which means that the odds in favor of candidate A winning the election are 5 to 3. Yeah, I know. What's the probability that candidate A will win the election? Okay, so the odds in favor of him winning the election, or her, are it's 5 to 3, and so it's 5 in the numerator. And then 5 to 3 is a total of 8, right? So, 5 plus 3. And so it's actually the case that the probability is 5/8. And so that's what you do. You take the two numbers that are the odds, and they go in as a sum in the denominator. And then there's the in favor of and against. And so we could turn this around and say, what's the probability candidate A will lose the election? And that would be 3 to 8. Okay? So that's how probability and odds are related.